Hi students, this is Dr. Madhusudan Rao. We begin our lesson on current electricity. This lesson starts with the concept of charges in motion. What is current? Current electricity is the study of charges in motion. Hence, it is of our interest to know the substances which allow charges to flow through them easily and which resist it. Accordingly, substances are classified as conductors and insulators. Conductors. The substances which conduct electricity easily are called electric conductors. Since positive charges cannot flow, the conduction of electricity is primarily due to flow of electrons. Hence, conductors have large number of free electrons. Example, gold, copper. All metals are generally good conductors of electricity. Insulators. The substances which do not conduct electricity are called electric insulators. Example, wood, rubber and mica. Insulators do not have free electrons. The rate of flow of charges is known as electric current. It is denoted by I. If Q is the net charge passing through any cross section of a conductor in a time t, then average current I is equal to Q by T. Current I is equal to charge Q divided by time t. Current is a scalar quantity. Current is not a vector quantity. It is a scalar because it doesn't obey the laws of vector addition. Current is a macroscopic quantity like the mass of a body or volume of a container. SI unit of current is ampere. 1 ampere. The current passing through a conductor is said to be 1 ampere when the net flow of charge per second through its cross section is 1 coulomb. The charge transferred is always an integral multiple of the fundamental charge of an electron. This property is referred to as quantization of charge. That is, Q is equal to N into E, since current I is equal to Q by T, or I is equal to NE by T, where E is the magnitude of charges of an electron, N is the number of electrons. It is our common observation that water flows from a place at higher level to a place at lower level, irrespective of the amount of water at the two levels. Heat flows from a body at a higher temperature to a body at a lower temperature, irrespective of the amount of heat contained by the two bodies. Similarly, electric charges move from one point to another if there exists a difference in the electric potential, irrespective of the concentration of charges at the 2 points. Thus, electric potential determines the direction of flow of current. Charges flow from a body at higher potential to a body at lower potential. By convention, a positively charged body is always at higher potential as compared to a negatively charged body. If positive charges like protons or positive ions are free to move, they would move from higher potential point to a lower potential point. Usually, the movement of charges implies movement of electrons. It is clear that electrons will move from a lower potential to higher potential. This constitutes electronic current. Since the convention is that flow is always from higher to lower level, the conventional current is taken opposite to the electronic current. It should be remembered that conventional current implies the movement of positive charges, whereas electronic current is the movement of electrons. We have already seen that charges move from one point to another if there exists a potential difference between them. Thus, whether the current is flowing through a conductor or electrolyte, a potential difference is necessary for it. Flow of electric charges in a metallic conductor. The free electrons present in the conductor are responsible for the flow of electric current. In a metallic conductor, on an average, there will be one free electron available per atom. At any temperature, these free electrons will be moving in all directions at random. The electrons in the conductor are continuously making random collisions with the fixed atoms or ions inside the conductor. The resultant velocity of the electron will be zero in any direction. As a result of this, the net flow of charge at the given cross section is zero. Hence, there is no net flow of current within the conductor. In short, the absence of external electric field, the motion of the electrons in the conductor is random such that the average thermal velocity of electrons becomes zero, that is U equal to 0. When an electric field is applied across the conductor, the free electrons accelerate in a direction opposite to the direction of applied field. Due to this acceleration, the electrons gain extra velocity, but for a short time, because the accelerated electrons collide with other free electrons or the ions in the conductor, and during this collision, the extra velocity gain is destroyed. The obstruction offered by a conductor to the flow of electric current is called its resistance. Again, the electron is accelerated and come to rest after collision. Therefore, the motion of electrons in a conductor under the influence of electric field is like a stop and go. As a net result, the electrons acquire a small velocity called drift velocity Vd in the direction opposite to that of electric field. The flow of electrons with drift velocity from one end to another end of the conductor constitute an electric current. The drift velocity is the order of 10 to the power of minus 4 meters per second, which is very small. Drift velocity. Drift velocity is defined as the average velocity with which free electrons in a conductor get drifted in a direction opposite to the direction of applied electric field. Consider a conductor under the influence of electric field E. The force experienced by a free electron in the conductor planned in the electric field is given by F is equal to minus small e into capital E. Negative sign shows that the direction of F and E are negative and opposite to each other. The acceleration produced the electron is given by A is equal to F by m, where m is the mass of the electron. A is equal to minus small e into capital E divided by small m. Mobility mu. Mobility of a current carrier is the ratio of the drift velocity Vd of a current carrier in a material to the applied electric field capital E. Across the material, that is mu is equal to Vd by capital E, where mu is equal to Vd by capital E, which is equal to meters per second divided by volt per meter, which is equal to meter square per second per volt. The conductivity of a material depends upon the charge carrier concentration, the number of charge carriers per unit volume, and the mobility of the charge carriers. Relation between electric current and drift velocity. A portion Kp of a metallic conductor to which an electric field capital E is applied from right to left side as shown in the figure. Let the conductor be of uniform area of cross section A. Let us assume that under the influence of the applied electric field capital E, all the electrons in the conductor are moving with the same constant drift velocity Vd. In a time t, let us assume that the free electrons move from cross section 1 to cross section 2. The distance travelled by the electrons will be L is equal to Vd into T. The volume of the region between 1 and 2 is V is equal to Vd into T multiplied by A. Let us assume that the number of free electrons per unit volume in the conductor be small n. The number of electrons crossing the cross section 2 in a time t will be small n, which is Vd into T into A. Consequently, the total charge Q crossing the area of cross section 2 in time is given by Q is equal to N into Vd into A into T into E, where E is the charge of the electron. By definition, the current I is equal to Q by T, and hence I is equal to N into Vd into E into A. Therefore, I is equal to N into E into A into Vd. Thus, the value of current I flowing through a conductor directly depends on number 1, the charge carrier concentration, the number of charge carriers per unit volume small n, number 2, the magnitude of charge of the charge carrier small e, number 3, the area of cross section capital A, and number 4, the average drift speed Vd. We have the drift speed is given by Vd is equal to I by N into E into A. The drift speed Vd is number 1, directly proportional to the current I, number 2, inversely proportional to the charge carrier concentration small n, number 3, inversely proportional to the magnitude of charge E of the charge carriers, and number 4, inversely proportional to the area of cross section capital A.